All right, so again, before we go on to any more of the limit process, we do have to make sure that you remember discontinuities because they do cause problems. So again, rational functions, again, that means there's some kind of variable in the denominator. They will have either non-removable or removable discontinuities, or they could have both. Non-removable discontinuities are called, asymptotes, because that's what we talked about yesterday. Okay? And the removable are called
Holes.
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 Okay? So holes, otherwise known as removable discontinuities, because you could have just read down here to get the answer. It's when factors can be canceled out. You get holes in the graph, and huge hint, that's why it's written a little bit bigger. Always look for those first before you do anything else. Right? Otherwise, you're going to get some false answers on vertical asymptotes if you don't look for the holes first. The reason I waited to do this particular one till the second day is I made sure none of the ones on the first day were going to have that happen. All right? So let's go ahead and let's try to determine any holes for this, and then we'll sketch it. And so again, remember, if you're going to look for any kind of, if you have a rational function, always look for holes first, no matter what you do. And so what we're going to do is see if there's anything I can cancel. And so we're going to say, well, really, this numerator does factor into x plus 3 and x minus 3. And the denominator is x plus 3, right? And so we do actually have a factor that cancels out, because no matter what x value I substitute in there and x value I substitute in there, it's going to be the same number, right? So any number over itself is just 1, so these factors do cancel. Okay, right? Agreed? But the problem is notice that's one of them that was here, and so there was a potential x value that could have caused a problem, correct? Would have caused me to divide by 0, but in this case I was able to remove it. Okay? And so you still want to find out, well, what causes that problem? So whenever you cross something off like that, find out what will actually make it equal 0. Because it's still a problem. It's still a discontinuity. It's just a slightly different one. And so the x value in this case, if we do the algebra, is negative 3. So we know negative 3 is still not part of the domain of this original function. Because I can't put negative 3 in there and get a result. Right? Nothing's going to come out. Now everything else is in the domain because nothing else causes a problem. But if we look back up here, this is all that remains. That's what's left over. And it's really that over 1, right? So what we have to worry about is, let's just try and graph that then. And once we graph that, then we'll go back to what the problem was, which was x being negative 3 was a huge problem. So to graph y equals x minus 3, I think we should all know by now that's going to be a line. Okay? A bunch of points that are combinations of x and y that make that true. So we could get a bunch of those points, or we could just kind of graph it like that. Okay, so there's that line, but you notice my line happens to have a hole in it. Okay, and notice where I put that hole when the x value was negative 3. And the easiest thing to do is, if I know this is a problem, why don't we just substitute it in here and find out where it would have been, and then just erase it and say, yeah, it's not supposed to be there. And so I put negative 3 in there and found out it is negative 6, and you can see that's exactly where I put that particular hole right there. So I know it's somewhat hard to believe, but this graph over here shows you all the solutions, all the combinations of x and y that will make that true. And so pretty much the domain is all reals except for negative 3. Okay, and the range is all reals except for what, negative 6? Right? Okay. So any questions on that in general right now? Yes? The question was, are we going to talk about multiple holes? And I think there may be an example later that does have more than one hole in it. Yep. And that can happen. And obviously, if we have a piecewise function, that could have tons of holes in it, right? And so I think one does show up in a second. You do notice the one thing I did here is I took the exact same stuff and just switched it over. All right, well, let's see what happens. Let's, again, look for holes first. Well, we've got this. We just found out that we've got that in the denominator. Agreed? Do we have a hole in this function? Yeah, huge hole, because this still cancels, right? But I still have a 1 in the numerator. Agreed? Once that cancels. So once again, whatever you cross off, you know it's still a problem. Okay, it will show you a value that will not be in the domain. Because if I substitute negative 3 in there, it has me dividing by 0, right? Okay. In this case, is that the only value that causes a problem? Last time it was, correct? I think we can see that also positive 3 still does cause a problem. So where did that go? Yeah, it's an asymptote, because do you agree that positive 3 still causes a problem over here? Okay. Now what I'm left with, if we look right here, is I'm left with something slightly different from last time. Is that a line like it was last time? No. That's a rational function, and luckily we spent some time working with parent graphs. That's just that 1 over x parent graph done, and what's been done to it then. Move to the right, 3. Or let's face it, could we go and find the vertical asymptote and horizontal asymptote like we did yesterday? Yeah, both ways would work, right? So here's x. You're telling me there should be an asymptote there? Oh, there it is. Probably should be arrows on that. And then what is the horizontal asymptote then? Did that get moved up, down, anything like that? Nope, or you could have done from yesterday, the bottom is bigger, right? And so it's automatically y equals. Uh-oh. Uh-oh. Malfunction. There it is. Y equals 0. Now, once again, one thing I actually do like to do, because let's face it, we know in general, don't necessarily graph it all yet, we know it's up here kind of, and it would be down there, right? That's from our parent graphs. But with holes, I like to be kind of accurate. And so what we can do is we know this one creates a hole. Okay? So why don't we put negative 3 in there and find out where it went? Because you can put it in there. It doesn't cause a problem. So where does it go? It's really 1 over then negative 6, right? We see that? So negative 3, so negative 1, 2, 3, and negative 1/6 would be right about there, correct? So that's where you have a hole. And then you can just draw the rest of it in. And then once we get, we could obviously use the graphing calculator to get a really good idea. But these will just get some sketches and know where stuff is. And again, remember, that's going to be pretty hard to see that hole on your graphing calculator. You would have to look at the table and make sure that it was actually, working out properly. But it would show you undefined at just that point. Okay, how are we doing so far? Good? All right. So that's holes. All right. Here we go. We've already discussed if the top and bottom are the same degree and if the bottom is bigger. That should lead you to the question, what if the top's bigger? Then would you agree that we've pretty much covered all options? They're the same, the bottom is bigger, the top's bigger, right? It's about all that can happen. So here's option 1. The top is exactly 1 bigger than the bottom. This is a very special case. If it's exactly 1 bigger. And if that happens, we will get a slant asymptote. Again, all of this is, after you found all those holes and gone through all that work, is that what you're left with? Okay. And the other one is if it's more than 1 bigger. The top's more than 1 bigger than the bottom. In this case, there is no slant or horizontal. Again, these are shortcuts I'm giving you here in finding these asymptotes. Doing it, I guess, more by hand is more finding an inverse and going from there. And we'll talk hopefully about why that happens so we can, figure out these for ourselves instead of having to remember these shortcuts all the time. So let's just try to determine if the following function have horizontal, vertical, and or slant asymptotes. So letter A, what do you think? Well, first thing I would do is look for any holes. Okay, do you see any holes out of there? Anything going to cancel out? Any factors going to cancel? No. And how about then any vertical? So something that's not in the domain. What is not in the domain? X being -5 is a huge problem. Remember, to find verticals, the easiest thing to do is set the denominator equals 0, so x equaling -5 is a vertical asymptote. And actually, this doesn't say that I have to find out what they are, does it? It just says if they have them. So does it have a vertical asymptote? Yes. Now, it's not going to have a horizontal and a slant. Okay, so which one's it going to have? This one, the numerator, is exactly one bigger than the bottom. Agreed? See that? 2 and then 1 for the degree, right? 1 up there, right? So think of it this way: as x gets big, the numerator, like a million, right? The numerator would be a million squared over a million, and then a billion squared over a billion. What kind of happens when the numerator is exactly 1 bigger is that the denominator tries to keep up. It can kind of keep up for a while, all right? And so that's when you get a slant asymptote, okay? It's when it gets more than 1 bigger that it can't keep up at all. So this one actually does have a slant asymptote. Okay. How about the next one? Any holes? Nope, no holes, no factors that cross off. How about any vertical? What are they? Because somebody said yes to that. It'd be positive and negative square root of negative 6, correct? So it has imaginary if you set the denominator equal to 0, correct? So does it have a vertical? No, it does not. You still have to be careful. You have to make sure you can actually find a value that makes it not work in the domain, but you can't find any. So is it going to have a horizontal or a slant then at that point? Yeah, it has a slant again. Slant asymptote, because again, the top is exactly 1 larger. 3 versus 2, correct? And this next one, how about any holes? Any holes? Nope. Any vertical? Any values that are not in the domain, in other words? Yeah, 0, right? I'm not allowed to put 0 in there, right? So yeah, it does have a vertical. And how about a slant or horizontal? Well, the top's more than 1 bigger, so again, put a million to the 4th over a million squared. It just can't keep up. So there is neither one, no horizontal nor slant. Okay. How about letter D? Any holes? I heard a yes. No? Which is it? I've heard both answers now. I believe there's at least one, because I can factor an x out of the numerator and an x out of the denominator. And then there's x plus 1, right, on the bottom. And then what am I left with up here? X squared minus 3x minus 4. So we know there's at least a hole, so that's gone. Okay. Now, what about x squared minus 3x minus 4 over x plus 1? Is there possibly another hole? If the numerator factors, does it? It has to multiply to be, multiply to be what? Negative 4? Add to be negative 3? Do such negative 4 and 1, I've been told. Is that correct? Negative 4 and positive 1? Okay, so let's use the shortcut then. So it's x minus 4 is a factor and x plus 1 is a factor. Again, the shortcut only works when there's a 1 out front. All over x plus 1. Agreed? So there's another hole. So I'm left with y equals x minus 4. Is that rational? Is that a rational function at this point? No, there's no variable in the denominator. So should I be looking for any asymptotes at this point? No, so here's the example of multiple holes. Okay, this is a line that has 2 holes in it. Okay, does this look like a line that has 2 holes in it? Not really, but that's what it is if you were to graph it on your graphing calculator. You would graph y equals x minus 4 and put a hole at negative 1 and put a hole at 0. Yeah. Very true, that's not a function, but equals alpha of x. There you go. So if we were to graph that, then it would happen. Yes. I was waiting for somebody to say that, actually. That's pretty sad. Yeah. Any questions on that one? A little bit trickier, right? Here we go. Determine all asymptotes and sketch the graph for that. So possibly somewhat misleading directions, correct? Because there might be a hole. Is there? Does the numerator factor? It has to multiply to be 1, add to be 1. Yeah, not happening, right? It doesn't work. So we have to figure out what type of asymptotes we're going to have. Will we have a vertical? Yeah, it's whatever's not in the domain, so set the denominator once you look for holes equal to 0. And so the value that is not in the domain is negative 2, right? So x equals negative 2 is, I guess I'll just move the graph down. X equals negative 2 is definitely a vertical asymptote. Now what? This is review, so who remembers how to find a slant asymptote? Setting the numerator equal to 0, no. Nice try, though. It was a shot. You took a chance. Yeah, actually do what the problem says. Actually divide it out. Okay? Which means take x squared plus x plus 1 and divide it by x plus 2. Can we do synthetic on this one? This is a good question. We actually can if we wanted to, right? Because it is a 1x here, right? Plus 2. It's not x squared. It's not something weird. So we can actually do synthetic, but I'm going to do it this way quick, and then we'll do it synthetic just to review both of them, okay? So x squared divided by x is just x. So x times x is x squared. X times 2 is 2x. You then do what in long division? Yeah, you have to change your side or subtract what you have. So it's 1x minus 2x is negative x plus 1. Bring that down, right? And so negative 1x divided by 1x is negative 1. So it's negative 1x minus 2. Change your sign. Woo, not that one. Sorry about that. That's negative. And what do we got? A remainder of 3. So plus 3 over x plus 2 is our remainder. Who remembers what we said about the remainder in this very specific case, in this very particular work? Yeah, it's negligible, correct? We don't have to worry about it. Why is that? Because as x gets really, really big, what happens to this fraction? Yeah, it goes to 0, correct? And so we are left with y equals x minus 1 is our slant asymptote. For those that want to do the synthetic, what goes in the box? Negative 2, very good. You got to take the 0 that comes from this. And we would have a 1, and a 1. Well, how about that? So bring a 1, yeah, splash effect. So it's negative 2 when you multiply, right? Do you change your signs in synthetic? No. So it's 1 minus 2 is? That wasn't a trick question. 1 minus 2, negative 1. Splash effect is positive 2. Look at that. The remainder still ends up being 3. How do you put the variables back in? You know, this is the remainder. That's the constant. This is x to the first, right? Look, do we get the same thing? Why? Because your remainder is still getting divided by that, so it is negligible again. So y equals x minus 1. Is actually not part of the graph, but it is an asymptote. Okay. And then to find out where things go, you could just get a bunch of points, right? Find a bunch of points that actually make the original true. That's where I would go when I have my points. Go back to the very original and find out what values come out of there. So go back to that one. But I'll do that for you. I got some like 0, half is a point. And so what actually happens is it kind of does one of these. And I got a few more points down here, but we'll just sketch it real quick. It does that down there. Okay, so what should you always look for first, though? Holes. Okay. Then once you've found those, look for any type of asymptotes. Remember, just because there's something in the denominator does not automatically give you a vertical, right? Because look at that letter B right there. We weren't given a vertical on that one because there was nothing real that would make that undefined. Okay. Questions? Yes. Yes. Nope. The question was, do we have to select the slant asymptote equal to 0? Now I can't even find them. They're in there. Okay. We don't, because we know there's combinations of x and y that are going to cause a problem. But remember, that's as x gets large. Is it possible that it could cheat and cross over a slant and come back to it? Yes, it can. Verticals are the only ones that cannot be broken because it's not even part of the domain. You're not even allowed to put that in, right? Okay. But slants can be. Yes? The question is multiple slants or multiple horizontal. It is possible, but it's not going to happen in here. Like a negative tilt to the slant? Yes. Could have a negative slope to it, yep. But you mean along with a positive slope? Yeah, that wouldn't happen, but you could have possibly more than one. Yep, exactly. It would be like y equals negative x minus 1. Would give you a negative tilt to it, yep. All I did is I went and graphed that line, y equals x minus 1, and I just didn't make it solid. I just knew it was like a boundary line. Okay. Everybody else good?